The double-slit experiment is one of the most profound and unsettling experiments in the history of science. It does not merely illustrate a curious feature of light, it forces us to confront the fundamental nature of reality itself. In the early 1800s, the scientific community was divided over the nature of light. Isaac Newton had championed the idea that light consists of tiny particles, or corpuscles. This particle theory explained reflection and refraction reasonably well, but it struggled with other phenomena, such as diffraction and interference. In 1801, the English physicist and physician Thomas Young devised an elegant experiment that would change the course of physics. He allowed a beam of sunlight to pass first through a single small aperture, creating a coherent source, and then through two closely spaced narrow slits before striking a distant screen. What appeared on that screen was not two bright lines, as a pure particle theory would have predicted. Instead, Young observed a beautiful series of alternating bright and dark bands, a clear interference pattern. This pattern is the unmistakable signature of waves. When two coherent waves overlap, they interfere. Where the crests of both waves coincide, they add constructively, producing a bright fringe. Where the crest of one wave meets the trough of the other, they cancel destructively, producing a dark fringe. The spacing of these fringes depends on the wavelength of the light and the geometry of the slits. Young's results provided powerful evidence that light behaves as a wave. For much of the 19th century, the wave theory of light, further developed by Fresnel and Maxwell, became the accepted view. Yet, at the dawn of the 20th century, a new revolution began. Max Planck's work on black body radiation and Albert Einstein's explanation of the photoelectric effect demonstrated that light is also quantized. Electromagnetic energy is absorbed and emitted in discrete packets called photons. In the photoelectric effect, light behaves like a stream of particles, each carrying a definite energy proportional to its frequency. The wave picture alone could not account for this, so the question returned with greater urgency. Is light a wave, or is it a particle? The double-slit experiment was taken up again in the quantum age, now with the ability to control and detect individual quanta. Modern versions can send single photons toward the double slits, one after another, with such low intensity that the probability of two photons being in the apparatus at the same time is negligible. Each photon is detected as a localized point on the screen. According to classical reasoning, each photon must pass through either the left slit or the right slit, and the accumulated pattern should consist of two bands. But that is not what happens. As more and more single photon detection events are recorded, the familiar interference pattern gradually emerges. The individual photons land in an apparently random fashion, yet their statistical distribution matches the intensity pattern predicted by wave interference. It is as though each photon travels as a delocalized wave, passes through both slits simultaneously, interferes with itself, and only upon detection materializes as a particle at a definite location. This is the heart of wave-particle duality. The experiment grows still more mysterious when we try to determine which slit the photon traverses. If detectors are placed at the slits to record which path information, the interference pattern disappears entirely. The photons now behave like classical particles, producing two distinct bands corresponding to the two slits. The wave-like interference is destroyed as soon as knowledge of the path becomes available. Crucially, this effect is not simply the result of a rough measurement knocking the photon off course. Sophisticated experiments have been performed in which the which path information is obtained in extremely gentle ways, or even stored in the internal state of the particle itself without significantly altering its trajectory. Nevertheless, whenever the experimental arrangement makes which path information available in principle, the interference vanishes. When that information is erased, the interference can be restored. What matters is the possibility of knowing the path, not a crude physical disturbance. In the mathematical language of quantum mechanics, the situation is described by the wave function. Before measurement, the particle is in a superposition of the two paths. The wave function components emerging from each slit spread out and overlap, producing interference in the probability amplitude. The probability of detection at any point on the screen is given by the square of the total amplitude. When a measurement is performed that distinguishes the two paths, the superposition collapses. One path is selected, and the cross terms responsible for interference disappear. The double-slit experiment is not restricted to photons. It has been successfully performed with electrons, confirming the wave nature of matter predicted by Louis de Broglie. It has been done with neutrons, with atoms, and even with large molecules such as fullerenes and complex organic compounds containing dozens or hundreds of atoms. In each case, under conditions of sufficient isolation from environmental disturbances, interference patterns are observed. Quantum superposition and interference are universal features of nature, although they become extraordinarily fragile as systems increase in size and complexity. This single experiment encapsulates many of the central conceptual pillars of quantum mechanics: the superposition principle, quantum interference, wave particle duality, and the active role of measurement. It continues to serve as a testing ground for interpretations of quantum theory. Different schools of thought, Copenhagen, many worlds, de Broglie-Bohm pilot wave theory, quantum Bayesianism, and others, offer different accounts of what the experiment is telling us about reality. Yet all must confront the same stubborn experimental facts. Beyond its foundational importance, the physics revealed by the double-slit experiment is now being harnessed for technology. Quantum computers rely on the controlled manipulation of superposition and interference. Quantum metrology and sensing exploit quantum coherence to achieve measurement precision beyond classical limits. The same phenomena that appear so paradoxical in the double-slit setup are becoming practical resources. The double-slit experiment stands as a gateway to the quantum world. It shows that at the fundamental level, nature does not obey the intuitive rules we learn from everyday experience. Objects can occupy multiple states or paths at once. Measurement is not a passive observation but a transformative act. The future is not fully determined until it is registered. And the universe, at its heart, is far stranger, more subtle, and more wonderful than classical physics ever led us to believe. Thank you for joining this exploration of the double-slit experiment. It remains one of the clearest windows into the quantum realm, a reminder that the universe is far more subtle and surprising than our everyday experience suggests. The next time you see a simple interference pattern, remember the profound questions it still raises about the nature of reality itself.